Okay, everybody, let's continue. Okay, gradient factor. So as I mentioned earlier, if the endurance, our Moore test is done under some very controlled test conditions, and anything that deviates from this specific test conditions has to be changed, has to be considered when analyzing an actual application. So the first condition is the gradient factor. So these samples have a specific diameter. And if the diameter changes, then we need to consider that when calculating the endurance strength. So the thing here is that if you have a big diameter, the possibility, well, you will have, first off, more cracks. So the possibility of encountering a crack, a minute crack, is bigger. Remember that we said that fatigue always starts when a zone of generally of high stress concentration meets a minute or a local crack, and hence um, a crack starts to generate and then to propagate. So first off, we have more cracks. That's one of the consideration. Second is if you see this stress gradient here, notice how in a small sample it drops very quickly in its values. So let's divide this in two zones. This is a cross section. So this outer from here outwards, just for understanding purposes, we're gonna say this is a highly loaded zone. And from here, a lower load zone. So lower load zone. You're gonna notice that the higher loaded zone is gonna be bigger because that gradient drops quicker in smaller samples than in bigger. So you will have more cracks exposed to higher values of stress in a higher sample, in a part of a bigger cross section than that of a sample. So we need to consider that gradient factor. Then we have the surface factor. So the surface factor considers that a mirror polished surface was used. So the first aspect is the diameter of the sample. Second is the surface finish. So if in my actual application, I am not using a material that has a polished mirrored surface, I have to consider that. Remember I said irregularities in the surface serve as stress concentrators, and this can be harmful impact. So here we're going to be using figure 8.13, which you can find in your textbook. And you have a different set of values for different surface finishes. The surface finish is going to be an input for you guys in order to determine the surface factor. And there's going to be two inputs. First, the strength of the material, the ultimate strength. And second, the surface finish. As well, you can enter the graph with hardness, the brittle hardness, or the surface finish. For example, I have a material of one gigapascal, and it's machined or cold drawn. So the surface finish is the surface factor would be 0.69 approximately. Now let's say that same material with that same strength, I change the finish to fine ground or commercially polished. It rises all the way to 0.9. So notice how a surface finish can impact significantly the strength of a material in fatigue. Gradient factor and surface factor. Um, the the way we are going to compute the endurance strength at 10 to the power of 6 is going to be the following way. So we're going to have Sn. So Sn is going to be my actual endurance strength multiplied by Sn prime multiplied by the load factor, the gradient factor we just saw, the surface factor, and then we have two other factors that we can use. We generally don't use them too much in this unit, but know that they are there. So there's the reliability factor. It's pretty straightforward. If I want a 95% reliability, I use a factor of 0.868, 99.9, 0.753. And if I want to keep increasing that reliability, the reliability factor is going to be increasing significant. I'm going to, for example, for a reliability of 99.999, like 3 nines, you get like a reliability factor of 0.553. So it really impacts the endurance. So you must be sure of what type of reliability you're using. So we spoke of the gradient factor. The gradient factor is when my sample deviates from the sample that I use for the armor test, the actual size, and it's based on the diameter. And so the armor test is done for a circular shaft, but we can also do it for a beam. So let's say I have this beam. This one would be this one. And it's being loaded like this. Then my gradient, the equivalent diameter, let's call it like an equivalent diameter, would be the distance between the opposing surfaces where the fatigue, the bending fatigue is occurring. So here would be, let's say, the maximum stress element in tension, and here, let's say, would be the maximum stress element in compression. So this distance, let's say if it's, I don't know, let's say 45 millimeters, then I come here and I say it's in between 10 millimeters and 50 millimeters. So I use this value. And then depending on the load, if it's bending, axial, or torsion. So in axial, for the gradient factor, there is another component. So if our part is mentioned to be a precision part, we use 0.9. And if they say it's a non-precision part, then we use 0.7. We use values in between. This basically means that if I have an element loaded as such, and if I take this cross section and I divide it into these different quadrants, and all these quadrants are exactly the same, perfectly symmetrical, then when I apply this load, the load is going to be perfectly centered. So my center of area, let's say, is going to be perfectly in the center. If this is not the case, if the center of area is slightly deviated from the point of application of the load, then bending loads are going to start appearing here in the in the when you're actually loading. So this factor takes into consideration the fact of the precision of fabrication of my part. Okay, so that is what it means. In an exercise, you might find it's a precision part or a non-precision part. Is it precision? 0.9, non-precision 0.7. And notice that it only applies for actual loading. Okay. So, okay, another one, the load factor. So bending and axial, we use the same. In torsion, you see 0.58. You probably remember this 0.58 from when we calculated the maximum shear strength at yield from the von Mises stress. So this is where it comes from. So the load factor for torsion is 0.58. And for bending and axial, we use the same 1 and 1. Gradient factor. So gradient factor depending on the diameter and the load as well. If it's smaller than 10 millimeters, we use 1 for bending, 0.7 to 0.9 for axial, and 1 for torsion. And bigger than that, then we use between 10 millimeters and 50 millimeters. It's 0.9 for bending and torsion, and 0.7 to 0.9 for axial. Okay. Any questions in this part? And S prime N, endurance strength from the RR Moore test, and Sn is the actual value of our endurance strength for our application. Okay, here are, so when we're gonna build an Sn curve, we need 2 points. We need Sn. Who can say what Sn is? Nobody? Sn. Yeah, but what does it mean? The value exactly? What does it mean? So yeah, so the maximum strength that can be submitted, applied to our part, that will allow for an infinite life. Okay. Anything below that will give an infinite life. So meaning that Sn is the stress at which our element will have an infinite life. And then we need to calculate our 10 to the power of 3 life. So we need those 2 points. And here is how you calculate the stress. So it's pretty straightforward. They call it here SF. So if I have a bending load, my point here would be 0.9 times the ultimate strength. If I have an axial load, my SF here at 10 to the power of 3 would be 0.75 times SU. And if I have a torsional load, I have SF of 0.9, ultimate strength at shear. And that is how I build the Sn curve. So this is an Sn curve. 10 to the power of 3, I have SF, and SF I calculate using these values. These values are all in, Tan, do you have a textbook? Second. So these values, you can find them in the following table of the textbook. Hey guys, another suggestion, please make sure you know how to navigate through your textbook, okay? Where are the tables, where are the figures, where are the equations? That's gonna save you a lot of times during the exam. I would even suggest to have a separate sheet with all the equations written down. It will save you some time, so you don't, and the graphs as well, so you don't have to go through one part or the other. Okay, so table 8.1 has all this information. It's this one that I'm showing, these 2 slides. And with this information, you can build an Sn curve, okay? Any questions about this? Or is everything perfectly clear? No, I'm fine. Like I know like everything might not be perfectly clear now, but please go through the slides. I'm going to upload some more exercises today. And there's some exercises in the text. Just go through them, and yeah, it should get easier. Okay, we're almost done with fatigue. How is sigma m in the RR Moore test? What's the value of sigma m in the RR Moore test? 0. Good. Oh, before we get to that, so anybody remembers if we use stress concentrators for ductile materials in static loading? Static loading, ductile materials. Do we use or we don't use stress concentrators? No, right? No. The thing is, in fatigue, even though materials are ductile, we do use stress concentrators, especially because we already said that they have a different behavior when they're submitted to fatigue loading. So opposed to static loading, when stress concentration is exclusively determined by the geometry, the ratios between diameters and notches. In fatigue, it depends on that factor. So we need to know KT. So this is our, let's say, this considers or accounts for the geometry, not shape, not size, geometry. But it also depends on the material. So that way we calculate a fatigue stress concentrator. So we have a stress concentration for static applications for brittle materials that is KT, and we saw last class how to calculate. And we are still going to use it. But we also need to consider a new fact. The fact is that not all materials have the same sensitivity to stress concentration. So in fatigue, it is also considered the sensitivity of a material to stress concentration. And for that, you're going to use this graph. This graph has two inputs, the notch radius. So let's say we have this. We need to know the notch radius, or if we have this, the notch radius depending on the geometry. And we need to know either the hardness or the ultimate strength. So for example, if I have a notch with a radius of 1 millimeter, and the type of load, and it has a, let's say I'm doing an axial load, I have a radius of 1 millimeter and a material of 140 KSI, and SU is equal to 140 KSI. So I go here to 1, and note that it says use these values with bending and axial loads, and use these values with torsion, which means this is an axial load, and it says 140 KSI, so I would use this value, this curve. So I would go wherever this curve intersects this one here, and I calculate Q. So that would be my notch sensitivity factor. And for this case, let's say it would be 0.82, say something. So then I chuck this in this equation. Then I use the KT that I calculated from my stress, from the other graph that we saw last class, and I calculate my fatigue stress concentration factor. Okay? So that is how you calculate KF. You use this graph, but you also need to calculate KT. So if you're not too acquainted with that, maybe go to the last class and yeah, learn. This is going to be in the exam, so you need to know how to do this, okay? You need to know how to calculate the stress concentration factor of the okay, you guys now know how to draw a 10 to the SN diagram. Okay, here we go. So R Moore test, sigma m is equal to 0. Sigma m equal to 0 means that you can compare the SN curve to your loading application. So the R Moore test gives us information to build an SN curve, but the R Moore test is done with sigma m equals 0. So when sigma m is different from 0, we're going to use something called the Goodman lines. And the Goodman lines will extend our comparison of all the other cases where sigma m is equal to 0, and will now allow us to have all the possible cases that we will encounter in reality and have a way to compare it. So this we already saw this graph. So here we have a load that is changing with a sinusoidal pattern. We here have the value of sigma m, which is clearly different from 0. And we here have a value of sigma a. Note that these two graphs have the same value of sigma a, but this one is higher. So which one has the bigger sigma m between these two graphs? Left or right? 1 or 2? Which one has the higher sigma m? 2. 2. Two loading patterns with an equivalent sigma a, but a higher sigma m, the one with the sigma m higher is going to be more harmful in terms of endurance for the material. So we need to consider that if we have sigma a with a higher sigma m, it's going to be more harmful. So the stresses are going to be higher, and we need to consider that. If, for a case, we wanted to continue increasing sigma m, but having the same life, what we would need to do is reduce the sigma a. So let's see point A. In point A, we have this sigma a. And this gives us infinite life, 10 to the power of 6 life. If we wanted to have a higher sigma m, in this one, sigma m in A, sigma m is equal to 0. Now we're going to increase sigma m a little bit. So sigma m went from here to here. If we want to continue having that infinite life, sigma a no longer can have the same value. You need to decrease slightly the value of sigma a. So you will still have 10 to the power of 6, but sigma a, let's say point A, sigma a equal to Sn, and sigma m is equal to 0. Then we go to point B. We increase slightly sigma m. So sigma m increased a little bit. Let's call it, I don't know, sigma. So we increased it a little bit. And in order to compensate for that increase in sigma m, we need to decrease sigma A. But we still have infinite life. So here we have 10 to the power of 6, and here we have 10 to the power of 6. If, for example, this was, we had this point A, and we would increase sigma m without decreasing sigma A, we would no longer have infinite life. The part would probably fail before reaching the life of the element. We can keep on doing this, increasing the sigma m and decreasing the sigma A in order to maintain that infinite life of the material. Notice that you can only do it so far because there's going to be a point where you're going to exceed the yield strength. So for example, if you do that, in one first cycle of application, you're going to have exceeded the yield strength, right? And sometimes exceeding the yield strength is going to be considered a failure, so you can't. But just for the sake of this exercise, we're just going to continue increasing it past the yield strength, past the ultimate strength, until only one cycle of application, we reach all the way to the ultimate strength. And what happens when we apply the ultimate strength? Yeah, necking occurs, the material breaks just in one cycle of application. So all this mumbo jumbo that I just told you guys is condensed into one graph. And it's called the Goodman lines, otherwise called the constant life lines. So in this axis, we're going to be graphing sigma A. And in this graph, I'm going to be graphing sigma M. Another exam question, by the way, probably. And now we have here 10 to the power of 6. What is the value of stress that I can apply to my material at 10 to the power of 6 with sigma m equal to 0? So if sigma m is equal to 0, what is the maximum sigma A that I can apply to have infinite life? So this would be the RR mortis condition. What would that be? Anybody? For sigma m equal to 0, what would be the maximum sigma A that I could apply to have infinite life? Sn. So in this axis, I have sigma A, and in this axis, I have sigma m. And if I'm moving along the sigma A axis, it means that sigma m is equal to 0. And if sigma m is equal to 0, I'm pretty much in the Sn curve. And all these values are from the Sn curve. Actually, all these values are from the Sn curve. So this is 10 to the power of 6, 10 to the power of 5, 10 to the power of 4, and 10 to the power of 3. By the way, if you want to, we already saw how to calculate 10 to the power of 3, the Sn value, the SF value, using these equations here. And we already know how to calculate Sn, this value here. And all those intermediate values you can calculate them by you simply figuring out the equation of this line and just computing the value. You have 10 power of 4, you can easily compute this value just using the equations of a line. Just remember, obviously this is going to be logarithmic scale, log here and log here. So don't make the mistake of computing the absolute, the value of the number is the logarithm of those values. Okay, so we said here that this here in this axis sigma m is 0, and in this axis sigma a is 0. But think about it. What does sigma a being 0 mean? Let's draw it. Let's have this load. This is sigma a, right? So if I make sigma a smaller and smaller and smaller to 0, what does that mean? It should become something, let's say, on a line, right? Which is static loading, right? So there's no fluctuation in the load. What is the value, maximum value then of static loading that I can apply to a material before it breaks? Which one? Breaks. Yield strength is for plastic deformation before total break. Ultimate, SU. So here we have SU. Sigma m equals 0 SU. And notice that this line has a decreasing slope, which means that sigma a is going lower and lower and lower until it becomes 0, until one cycle of application breaks my material. But there's also yield strength here, SY and SY. And this is a 45 degrees, so it has a slope of -1. It's relevant to identify if your material is going to fail first by yielding or by fatigue. And then you can also do this for if this for 10 to the power of 5, 10 to the power of 4, and 10 to the power of 3. To not get too complicated, we're going to limit this to 10 to the power of 6 to infinite life, okay? So now you know how to draw the Goodman line diagram. So if you have, for example, you have determined your sigma a value. So remember, you already drew your graph and you have sigma a, and you already have sigma m. What you do next is that you plot it. Let's plot two values here. Right? So here's our sigma a, and here's our sigma m. And we're going to draw what is called a load line. So the load line has this slope. And this slope is nothing but sigma a divided by sigma m. And wherever this line crosses the 10 to the power 6 constant lifeline, that's going to be our failure point. So there's some things we can do here. Obviously, you need to calculate the equation of this line. It's very easy. So in the y-axis, we have sigma a, right? So the equation of this line is going to be sigma a is going to be equal. So who remembers how to calculate the slope of a line, the m? So let's say we have 2 points. So we have this point. This point is SU, comma 0. And we have this point here. This point is 0, comma SN. If we do 0, sorry, this is, yeah, 0 minus Sn over Su minus 0, this is going to be minus Sn over Su, the slope. Or it's a negative slope. It makes sense because it's decreasing, right? Then we also need to know the intersection point with sigma A. So if sigma m is equal to 0, what is the value of sigma A in this axis? When sigma m is equal to 0, what's the value of sigma A? Sigma m equal to 0, Sn. So sigma A is going to be equal to minus Sn divided by Su times sigma m plus Sn. Yeah, that's pretty much it. So that's the equation of your Goodman constant lifeline. And the equation from the load line is pretty much sigma A equals to sigma A. Well, the slope is this, but this you can also calculate it. Sigma A over sigma m, and then you can have the equation of this line. So it's gonna yeah, and then you can compute where is this intersection point. Using these two lines, you compute the intersection point. Then you come down here, and you have your value of sigma m. So your safety factor is going to be equal to this computed value here. Let's call it S N M, and this one here is S N A. So it's the endurance strength in the A axis and in the M axis. So this length here divided by this length here is your safety factor. So since these are similar triangles, this length here up to this point divided by this length here up to this point is also your safety factor, and this point here over this point here. So you can use any of those three relationships to calculate the safety factor. I think this is more overwhelming when it's seen like this. It's not. It's just pretty much this is like algebra. So it's very simple. Just knowing how to build a diagram. We're gonna do an exercise in a moment, and hopefully it'll be clear for all you guys. Okay, finally, the Palgrim and Minor rule. So what this says is that when an element is stressed at a certain, sorry, it's fatigued at a certain stress level. I think it's enough. Let's just we'll continue this part next class. And what time is it? Yeah, maybe take 15, 10:45. It's been so long. Yeah, take 10. Let's take 10-minute break, and then we're gonna do an exercise, which I think is very important for you guys. Okay. Please try and be on time, so because we're very short on time.